Hey everyone, this video lecture is going to cover the first half of section 7.4. That is, we'll talk about how to calculate the arc length of a curve. So we know that we can calculate the length between two points in space, but how do we calculate the length of a curve? Something like this. Say we have this curve, something like that. Let's say that this is x. Let's say that's A. Let's say this is B. Okay. All right. So one way that we could approximate the length of this curve is by a straight line, right? So we would have this line here. Could give us an approximation to the length of this curve. Of course, the curve would be much longer. If you were to stretch out that curve, it would be longer than that purple line I just drew, right? So this approximation to the arc length of the curve is not a very good one, right? So what we can do is maybe make two, instead of using this one line, let's use a couple of different lines. So let's call this x0, let's call this xn. Okay? So we're going to do our approximation techniques that we've been doing, right? So another way to do this would be to use maybe two lines. So in another point on the curve here, use two straight lines here and here. Right? Let's say that that was some other x value, x1. Right? We could, so the sum of these two line segments would be the approximation to the arc length here. You can see again that it's probably a better approximation than the one before, but it still doesn't get to the heart of the true arc length. So you guessed it, we can just make more and more points and draw these line segments, right? So if I have a point, let's say right here and right here, let's call that x1. Let's redefine this as x2. Say that's x3. Then we approximate using four lines instead, right? So you can see the more and more that we do, the more it fits to the curve that we're trying to calculate the arc length for. So this is our motivation behind the arc length, okay? So let's try that again. How do we calculate the length of these line segments? I'm going to redraw this. Say that's A or x naught. And then here B, which is, let's say, xn. Okay? What we're going to do is partition this axis. Say that's x1. And then I'm going to go the same distance away. Let's say that's x2. So on and so forth. So the one right before this would be xn minus 1, xn minus 2, and so forth, right? So how do we calculate the length of this approximating line segment? So let's look at the first one here. How do we calculate the length of that line right there? Well, we have, we know that we've partitioned the axis down here in such a way that all of these distances are the same. So we're going to call, this is our delta x, right? That would be our delta x. And we can actually use a right triangle to get the length of this line segment right here, right? So we know that the distance here would be delta x. right? What would this distance be? Well, that's the difference in the function values there, right? So this would be f of a or f of x naught, or let's say y naught, right? And then this guy here would be f of x1, or let's say y1, right? Same thing. So this distance we can define as delta y 1, right? Delta y 1. So why do we put a subscript on this one? Well, if you look at the next approximating length here, this guy, to get the length of that line, of course, we would have to use another right triangle, right? Delta x is going to remain the same because that's the same partition along this axis down here. So our bottom value here would be delta x again. But you can see that this distance for the change in y's is different from this distance here. So this would be our f of x2 or y2. And you can see that the difference of y1 and y0 is different from that of y2 and y1. So we need to keep those different from one another. So let's call this guy delta y2. And we'll do that so on and so forth for the remainder of the points that we're trying to approximate. Here would be another right triangle, another right triangle here, and then another one here. So to generate the overall arc length, right, the overall length of that red curve, we can approximate it by the sum of all of these lengths. Well, how would we get this length right here? Well, we would just use the Pythagorean theorem. So let's call this guy length 1. So length 1 would be, so length 1 squared would be delta x squared plus delta y1 squared, or L1 equals the square root of delta x squared plus delta y1 squared. L2 would be gathered in the same way, that length of this purple line segment here. L2 would then be the square root of delta x squared plus delta y2 squared, right? That side squared plus that side squared, square root gives us that there, okay? So if I say that my overall arc length, let's call it L, the length of that entire curve, is equal to the sum of all of these square root terms, right? Square root of delta x squared plus delta y1 squared plus L2, which is this guy, plus the next one, you can probably guess from the pattern, and it's delta x squared plus delta y3 squared, plus so on and so forth until the very last one, which would be delta x squared plus delta yn squared. Okay? Oh, and of course, the L is approximately equal to that, right? We still haven't got it exactly, because there will still be some error from our approximation. So the arc length L that we're looking for is only approximately equal to the sum of all of these lengths. Okay? So let's continue to kind of simplify this a little bit. This is going to be equal to, that's the sum of all of these like things, so we can represent that as a summation. So the summation, let's say I goes from 1 to n of the square root of delta x squared plus delta yi squared. So it's the sum of all of these small lengths. Now, we know we're going to have to incorporate an integral into this. Of course, this is calculus, right? By inducing a limit and taking n to infinity, right? But before we do that, we want to make sure that our form here is set up nicely. So note that our delta x squared, which is just going to end up being dx, needs to be outside over here, right? So what we can do is just manipulate this a little bit to get what we want. So it's the summation, I goes from 1 to n. I'm going to factor out the delta x squared from the inside of this radical. So what I'm going to get, if I factor off the delta x squared, I'm going to have two terms in this set of parentheses. If I multiply back, I need to generate this equivalent statement up here. So delta x squared times 1 would give me delta x squared plus, now if we think here, delta x squared times what gives us delta yi squared? Well, that would be delta yi squared over delta x squared, right? So again, if we go back and check, if we were to refoil that, we would get exactly the line before it. Okay. So now I can take the square root, because this is a product here, I can take the square root of each of these and multiply them. So finally we get sum I goes from 1 to n of, I'm going to write this term first, 1 plus delta yi squared over delta x squared times the square root of this guy, which is just delta x. Now again, you can see that this is still only approximately equal to the arc length that we're looking for. So again, we're going to induce a limit to help us get it exactly. Therefore, arc length for L is equal to the limit as n goes to infinity of this infinite sum. So we know from previous classes that the limit, the infinite sum here can be rewritten in a more compact notation. So the integral between our two endpoints, which we can go back to a's and b's, of the square root of this guy. Now remember, when we go to the infinite limit, this guy goes to 0, so we're going to use these differentials to rewrite the deltas here. So we'll have the square root of 1 plus dy squared over dx squared times dx. And if you notice here, if these both are being squared, we can actually rewrite that as square root of 1 plus dy over dx squared dx. So you can see here this dy dx is just simply the first derivative of the function y, right? So square root, the integral from a to b of the square root of 1 plus f prime of x squared. Okay. So this, either of these two forms, give us the formula for our arc length. Okay. All right, so let's try this example. Find the arc length of the graph of f of x x equals x to the 3/2 on the interval 0 to 2. So all we need to do is just utilize our formula. We need to find our f prime of x first. So let's do that first. F prime of x is equal to the derivative of x to the 3/2 would be 3/2 x to the 1/2. Right. So our arc length is equal to the integral from 0 to 2 of the square root 1 plus our derivative squared. Okay. Now all that's left to do is to simplify this thing. So let's see what we can do. 0 to 2. We can square this out. Let's see what we'll get. Square root of 1 plus 3/2 x to the 1/2 squared is 9/4 x to the first. So 9/4 x. Okay. So all that's left to do is try to figure out how to anti-differentiate this guy. Well, we notice that can be rewritten as 0 to 2, 1 plus 9/4 x to the 1/2. And we run through our techniques of integration. Is this a basic formula? No. Can we do any algebra on this? No. Can we do a u sub? Yes, we can do a u substitution because we only have this linear term on the inside, right? So let's go ahead and do our u sub. U would equal 1 plus 9/4 x. Du is 9/4 dx. Of course, we want just the dx, so let's put our 4/9 over to the other side. And recall that with u substitution, we also need new boundaries on the integral. So our upper bound will be u equal to 1 plus 9 over 4 times 2. 1 plus 9/2 is 11/2. Our lower bound will be u equal to 1 plus 9/4 times 0, which is 1. So our substituted integral will become the integral from 1 to 11/2 of u to the 1/2 du. Not 4/9, that is. Let's pull that out. So let's see what we get. 4/9 times increase and divide. So 2/3 u to the 3/2 from 1 to 11/2. So we'll have 4/9 times 2/3 times 11/2 to the 3/2 minus 2/3. So let's use our calculator to get that final answer. So it looks like about 3.53. Okay. All right, let's try another example. So same thing. Find the arc length of f of x equals 1/8 x squared minus the natural log of x from x equals 1 to x equals 2. So from x equals 1 to x equals 2. Alright, so we're going to need to find our derivative first. What is f prime of x? Well, here we'll have 1/8. 2 times 1/8 would be 1/4 x minus the derivative of the natural log is 1 over x. So arc length will be the integral from 1 to 2 of the square root of 1 plus 1/4 x minus 1 over x all squared dx. So you can see that the integrand is complicated at times, right? So a lot of the time we're going to have to use technology to actually calculate this value, but I believe this one can be done analytically. So let's try and do that, okay? So what I'm going to do is just FOIL out this ugly square here. So integral from 1 to 2 square root of 1 plus, and when we square this, we're going to get a 4th x times a 4th x, which will be a 16th x squared. 16th x squared. Then we're going to have 2 of this product, which will give us 1/4 x times 1 over x is just a 4th. So we'll have -2 of those, so -1/2. And then lastly, we'll have plus 1 over x squared dx. So we can see we have like terms here and here. So we'll have the integral from 1 to 2 of, let's do square root x squared over 16. 1 and a -1/2 make a +1/2. And that's 1 over x squared. Dx. Alright, so this one looks a little ugly, but what we can do here is do a little bit of factorization, right? So what I'm going to do is factor out 1 over 16x squared. Well, here's how I do that. So I'm going to factor out 1 over 16x squared. It's going to pull off the 16 from here, it's going to pull off the x squared from there, and it's going to create some nice whole number values at the top. So if I take off a 16x squared here, let's think about what I need to multiply back to get x squared over 16. So our 16 is taken care of. We would need x to the 4th here, because x to the 4th over x squared would give us x squared. Plus, now let's see here. What do I multiply to get 1/2? That would be it'd have to have an x squared in it, right? Because that's going to cancel. And then we want to make a 2 down at the bottom, so we would have to have an 8 right here. And then what do I multiply 1 over x squared by? What do I multiply 1 over 16x squared by to get 1 over x squared? That would be 16. Okay. So this is nice. You can see that this will factor into a perfect square trinomial, right? So our integral becomes 1 to 2, the square root of 1 over 16x squared, times this FOILs to x squared plus 4 all squared. So finally, I have the integral from 1 to 2. Note both of these things can be square rooted, so I'll get 1 over 8x from that, and then just x squared plus 4 from that. So one last simplification gives us 1/8 x plus 1 over 2x dx. Anti-differentiating will give us 1/16 x squared plus 1/2 the natural log of absolute x from 1 to 2. So you get 4/16 or a fourth plus 1/2 the natural log of 2 minus 1/16 plus 1/2 times the natural log of 1 is 0. So our exact solution, 1/4 minus a 16th will be 3/16 plus 1/2 the natural log of 2. All right, last example. So here we just want to set up, but do not evaluate the integral that finds the arc length of f of x equals x to the 10th minus cosine x from 0 to 1. So here we just want to set it up, but do not evaluate. So let's see what we can do. Arc length. First we need our derivative, right? So f prime would be 10x to the 9th minus plus sine x, right? That's the derivative of f. So our integral will be integral from 0 to 1 of the arc length, let's call it L, equals the square root of 1 plus 10x to the 9th plus sine x squared dx. And of course we could use technology to get that, but here we don't really necessarily have to do that. All right, that's it. So go ahead and try the suggested homework problems. If you have any questions, you feel free to email me, or we can set up a Google Meet session for office hours. Just let me know if you would like to do that.